And we're having a good time, having a good time. Doing quiz problems, we're having a good time. We certainly can. Can. All right, good. Quiz 10, woohoo! We are back doing more integration problems and life is good. So let's get right into it. Okay, number 1. Rewrite the iterated integral. So we're going from 0 to 2, 0 to 4 minus x squared, 0 to 4 minus y, f of x, y, z, dz, dy, dx as an iterated integral with order of integration dx, dz, dy. Okay, well, so that says we kind of know what the answer is going to look like. It's going to look like an integral, 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 and then we're going to have our f of x, y, z, and then it's dx, dz, dy. Okay, good. Look, we already got the answer, right? Ha ha ha, not yet. Got to fill in those bounds. Of course, that's the hard part. Okay, so this is really about changing the order of integration on a triple integral. Now, what's the process? The first thing is we have to understand, well, what does this shape look like? So let's start by describing the shape. So work from the sort of outside in. We know that x is going from 0 to 2. All right, that's not so bad. In fact, we can draw that. It says go from 0 to 2, right? Easy. All right, next layer. Y goes from 0 to 4 minus x squared. So 0 less than or equal to y less than or equal to 4 minus x squared. All right, so if we start with something one-dimensional, now we're to something two-dimensional, x, y. So we're going 0 to 2. They're going from y equals 0, which is down here, y equals 4 minus x squared. Well, if y equals x squared is the parabola, the minus turns it upside down, and the 4 shifts it up. So it looks like that. Okay, so our region is this shape. It's a parabola from 0 to 2. And of course, you should verify that indeed at x equals 2, you get y equals 0. That's not so hard to convince yourself. Okay, last level. Our final layer of our onion, that is our integral problem. Z, well, that goes from 0 up to 4 minus y. So let's figure out what's happening here. So we have our x, y, z. And now what we can do is we can get a good understanding of what's happening. Because this picture here, I'm going to sketch it down here. So we have 2, we have 4, and we have this curve coming down. Okay, so that's this curve is that curve right there. And so that shaded region is this shaded region. All right, so there's our bottom. In fact, it really is our bottom. Because notice, we're starting at z equals 0. So z equals 0, that really is the xy plane. Okay, cool. That's the bottom. Then we're going to go up to something. Now, what do we go up to?
What can I do for you?
Well, we're going to go up to the plane z equals 4 minus y. Now, you might not think of this as a plane right away, but it is. Okay. Think of it, suppose you were in the yz plane. Z equals 4 minus y. Well, you'd have 4 here, then you'd have 4 down there. Now what happens is there's no x. You know how I can tell? Because there's no x. That was the first clue that there was no x. Now, so what does that mean? It means that you just translate this back and forth. So we're just going to do a little translation. I'm going to put a little dotted line here. Okay, so there's a part of the plane. Now, what do we want? Well, we want to go from the bottom up. So we're going to come up here. And now what's going to happen is, as I come up, I'm going to actually start swinging around. Okay? So there's our shape. So there we go. Now what are our surfaces? Well, this top surface, that's z equals 4 minus y. The bottom surface, that's z equals 0. this back surface here, on the back side, that's a little triangle. That corresponds to x equals 0. This sort of square-looking thing, that's y equals 0. Then you have this curved thing. Now, what is that curved thing? Well, if you think about it, that's coming from that curve right there. You can see it's just going straight up and down, so there's no z. So this last surface, that's y equals 4 minus x squared. Okay, so there's our shape. Good, good. All right, now we need to start figuring things out. Now, dx, dz, dy, that tells me the last thing I'm going to figure out is my x. So, how am I going to begin? I'm going to begin by looking straight down my x-axis. So imagine I come in and I pick it up and I turn it so I'm looking straight down the x-axis. And if I do that, what will I see? Well, what I'll see is that the x-axis, not the z-axis, I'm not going to see the x-axis anymore. It's just a single point. But I'll still see the y and the z, and in particular, I'm going to see a nice triangle shape. Intersects here at 4 and 4, and this is the line z equals 4 minus y. Okay, cool. Well, now we can start answering some questions. So, our outer layer is about y. Well, let's look at our picture here when we look down the x-axis. Where does y go from? Well, y goes from 0 to 4. So that's our first layer. Now, how about z? Well, I imagine that I've picked a value for y, and I asked the question, where does z go from? So I go from the bottom part, which is z equals 0, up to the top part, which is z equals 4 minus y. All right, good. So now I've done the y and the z. My last layer is x. Now, how do I figure that out? Now, that one, it's not quite so obvious when you get to the last layer. Let's go back to our three-dimensional picture. Now, when I'm integrating with respect to x, or maybe I should say when I'm looking at my bounds with respect to x, that means I'm going to be moving parallel to the x-axis. So I'm going to be moving backwards and forwards here. So if I think about what I'm doing, I'm going to start on that back face and move to that front face. So the back face, that's this plane, x equals 0. So that tells me that this bound is 0. Now the front is this surface, y equals 4 minus x squared. Now it's not a plane, it has some curve to it. Now, do I put 4 minus x squared, and why not? You're right, I don't put 4 minus x squared. Good. Why? Well, why not? Because see how this is attached to dx? So I need it to be x equals something to x equals something. So I got to solve for x. Well, that doesn't sound so bad. You can say x squared equals 4 minus y. Take the square root. X equals plus or minus the square root of 4 minus y. But we don't need to think about plus or minus because we are definitely in the plus part. And therefore, square root 4 minus y. And that's our last bound. And we're done. Because we can't integrate it, we don't know what f is, and we weren't asked to integrate it. We were only asked to set it up, and we've done that. Good. Good. All right. Number 1, done. Okay. Next one, number 2. Ooh, it looks like something similar. So, 0 to 6, 0 to 4 minus 2/3 x, 0 to 2 minus 1/3 x minus 1/2 y, f of x, y, z, dz, dy, dx, and we're going to change it to dx, dy, dz. So again, we can write down at least some of our answer. It's going to look like integral, 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 and f of x, y, z, dx, dy, dz. All right. So there's our answer. Now we just got to do the work, and then we're done. All right, well, that's not so bad. I mean, we enjoy working. That's why we're in these classes. Now let's just sort of remind ourselves. We could have done this on the last problem as well. But just so we don't get lost, so the outer layer is x. So I can write this as x equals 0, x equals 6. Next layer is y. Y equals 0, y equals 4 minus 2/3 x. And the last layer is z. Z equals 0, z equals 2 minus 1/3 x minus 1/2 y. Because that's really, when we do our bounds, that's really what we mean. We oftentimes we don't do that, and when we don't do it, we sort of forget that that's what's actually going on. So let's dig into this. So we know that x goes from 0 to 6. Well, okay, that's not so hard to draw. 0 up to 6. Now, y, what does that do? Well, y, that's going to go from 0 up to 4 minus 2/3 x, because that's what that bound is telling me. 0 up to 4 minus 2/3 x. So now, the two-dimensional picture, x, y, this was just x. 0 to 6. So y equals 0. Then we have 4 minus 2/3 x. Well, we can figure some things out. For example, the intercept here is at 4. And then let's see what happens over at 6. 2/3 times 6, well, that's 4. 4 minus 4 is 0. Ah, perfect. Nice little triangle. Almost as if they had planned it that way. Because, true fact, they planned it that way. All right. So, nice. So, okay, we got our nice little shape going here. Life is good. Now, what's next? Well, z, right? So the last layer, 0 less than or equal to z, less than or equal to 2, minus 1/3 x, minus 1/2 y. Okay, so here we go. Here's our picture. Three-dimensional, x, y, z. So we're going to have 6 here, 4 here, and then we have this base. So what I'm doing is I'm translating that picture into this picture here. All right, so there's our base. And in fact, this is a pretty good picture, because if we think about our bounds, we're going from z equals 0. Well, that's the xy plane again. Okay, well, where do we go up to? All right, well, that's a good question. So, well, let's find the answer. We go up to z equals to minus 1/3 x minus 1/2 y. Now that maybe isn't the most obvious thing, but we can rewrite it. So one thing we could do is you could write it as 1/3 x plus 1/2 y plus z equals 2. Now if you write it like that, you say, ax plus by plus cz equals d. That is definitely a plane. Okay, good. This is something that should be plain and simple, right? Now, how to draw that plane? That's a good question. But don't worry, there's a good answer. Divide by 2. Now, you're probably thinking, that doesn't sound like a good answer. Well, hold on, there's more to the answer. So, a 6x plus a 4th y plus a 1/2 z equals 1. Now, what's going on here? Well, if you're going to draw a plane, you just need to know 3 points. So what I'm going to figure out is, where do I hit the 3 axes? Because if I know where I hit the 3 axes, that's 3 points, and life is good. So let's start with the x-axis. If I'm on the x-axis, what's true? Well, one thing that's true is x can be anything it wants, because you can move x backwards and forwards. But what about y and z? They're 0. So, if I'm on the x-axis, it's like I don't even see y and z. I can cover them up. So we get 1/6x has to equal 1. So where do I hit the x-axis at? That's right, at 6. Right there. Aha! That's a point on my plane. Good. Now, how about the y-axis? Okay, cover up the x and z. there we go. 1/4 y has to equal 1. Well, y equals 4. And the z-axis, cover up the x and the y, a half z equals 1, which means it's going to be here at z equals 2. So those 3 points are my plane, and so in particular, if I were to connect them, making this triangle, that would be the surface. Okay, so here is the other plane. So if you think of the pink plane, that's the bottom, and then the green plane, that's the top. Now, of course, this is just a matter of perspective. So what's our shape? Well, our shape is what we would call a tetrahedron. And in particular, it's this tetrahedron here. So if you go from the origin, so we have 4 sides. And 3 of them are really easy. This bottom side here, that's the side z equals 0. This side back over here, that's the side of x equals 0. This side, again, the back side, it's y equals 0. And this front side is this plane. All right, so now we've drawn our shape. We've labeled all our surfaces. Life is good. Life is beautiful. Now we just got to start thinking about how do we get our new bounds. So, dx, dy, dz. My innermost layer is x. So if I'm thinking about the bounds, I'm going to look down the x-axis because I want to figure out that axis last. So we're going to look down the x-axis, and if we look down the x-axis, what do we see? So we've picked up the x-axis, we've turned it, we're looking straight down, and lo and behold, we won't see the x-axis anymore. We'll just see something in the yz plane. There's our x-axis, it's that single point. Do you see what shape we're going to see in the yz plane? It's this back triangle. So, z equals 2, y equals 4, and there's our shape. All right, now we can start to figure things out. All right, let's start with our outermost bounds. Okay, so our outer layer is z. Where does z go from? Well, the lowest value is at 0, and the highest value is at 2. 0 up to 2. Now, I figured out z. The next thing is y. So, I imagine I'm at a particular value z, and now I'm going to go back and forth. So where does y go from? Well, I go from y equals 0, that's not so bad, up to some curve. So I need to figure out what that curve is. Now I can actually make it easy. There's 2 ways to do it. One way is, well, I can think of this as a line. I can say, well, if this is a line, I could say, well, z equals the y-intercept 2, and then the slope, well, down 2 over 4, so that'd be minus 2x, yes? I think so. Is that right? No. A half, ha ha ha. Rise is 2, run is 4. All right, 2 minus a half x. Then I can say, y. That's not x, that's y. Can't believe it. Classic Butler mistake. A half y equals 2 minus z multiplied by 2. Y equals 4 minus 2z. So that's that line. Y is a function of z. And why do I need a function of y? Because it's balanced in terms of y. So that would be 4 minus 2z. Now, if you don't like that, here's the other thing you could do, is you can say, well, look, take this plane, and what's happening here is that plane will turn into this line at x equals 0. So I'm going to take 1/6x plus 1/4 y plus a half z equals 1. And now, when I plug in x equals 0, this becomes 1/4 y plus 1/2 z equals 1. Now solve for y. 1/4 y equals 1 minus 1/2 z, and multiply by 4. Y equals 4 minus 2z. Now, it shouldn't surprise us that we got the same answer both times, because there's only one answer. Now, our last layer, the x. Let's come back to our three-dimensional picture. Again, if I'm integrating with respect to x, I should move parallel to the x-axis. So here's the x-axis, so I'm moving backwards and forwards. So as I move backwards and forwards in this picture, I'm going to hit on the back side one surface, and on the front side another. Now the back surface, that's easy to spot. That's x equals 0. So that's our 0 bound. Now the front side is that slanted surface. So we're going to hit that surface. Now, how do we write that? Well, we don't put this equation into there because it's an x. We need x equals. So we're going to now solve for x. So we get 1/6x is equal to 1 minus 1/4 y minus 1/2 z. Multiply through by 6. X equals 6 6/4, also known as 3/2 y, and minus 3z. So that's what goes up here. 6 minus 3/2 y minus 3z. And done. Done. Ah, this is fun. It's fun to draw pictures. You know, you kind of think like, hey, I'm an engineer, or I'm a scientist. I'll never have to draw. But you know what? I think engineers and scientists, they actually are very artistic people. They just hide it. And it's nice to let it out every now and then. Okay. Nice. Okay. Find integral 0 to 1, 0 to 1, 0 to 1. Ooh, that's really slick there, right? Y squared x e to the xyz dx dy dz. Now, if you think about our shape is kind of very uninteresting, at least compared to the last couple problems, because what's the shape look like? Can you see it? It says you go 0 to 1 in all directions. So what our shape is it's a cube. Now, what's the nice thing about cubes? Well, the nice thing is we can just change the order arbitrarily. So the question becomes, which is the right order? So we should choose. Now, one thing is we could do the current order, but you should be suspicious, because if we were just asked to do the integral in the order given, that seems too easy. We've been doing these problems for a while. We've grown very suspicious. It's not just enough. They got to make it a little bit more challenging for us, right? But let's think of it a different way. Let's make it easier for us. Okay, so suppose we had the question. You have y squared x e to the xyz. Would you want to integrate with respect to x, to y, or to z first? And which one would you choose? Why would you choose that one? Well, here's what I notice. If I look at the y's, there's a couple of y's. If I look at the x's, there's a couple of x's. When I look at z, aha, good news, there's just the one. Now, what is that telling me? Well, the fewer variables, oftentimes the easier it is to work with. So, let's integrate first with respect to z. Now, because it's a cube, it's really easy to change the order of integration, because it's just going to be 0, 1, 0, 1, 0, 1. Well, no matter which order we do things in. Y squared x e to the xyz dz. Now, that's not how you write a z. There's how you write a z. How about the next layer? Well, we can always change our mind later, but I'm going to go out on a limb and say maybe an x, because that seems a little bit slightly easier. So let's try dz dx dy. Okay, so we integrate that with respect to z, which means that we're going to treat our x and y as a constant. So we still have the y squared x, because that's our constant, e to the xyz. Then we're going to be dividing that by xy. Evaluate that from z equals 0 to z equals 1. All right, so we need to simplify that before we go any further. Now, one thing that simplifies is we get some cancellation. The x cancels with the x, the y cancels with the y. Woohoo! Nice cancellation. We like it when a plan comes together. So what do we have left? Well, we have 0 to 1, 0 to 1. Now when we plug in z equals 1, we're going to get the y in front, e to the x times y times 1, which is e to the xy. Subtract, don't forget, you got to plug in z equals 0. Because it's not going to be 0. It's going to be e to the 0, which is e to the 0 is 1. So subtract y. And now we're going to integrate that dx, dy. And that doesn't seem so bad, so let's integrate that. Notice that the dx integral here is actually not bad because there's only a single x. This one does even better. No x's. You can't, if there's one x, you can do better than 1, which is 0. Okay, so what does that integral become? 0 to 1. The first term, well, y is the constant. Then it's e to the xy. Divide by, you got to compensate for that constant upstairs. So divide by y. Then integral of y, well, that's our constant times x. And evaluate x equals 0 to x equals 1 dy. Again, we get some nice cancellation going out there. So we like it when things cancel. We plug in x equals 1. And what does that give us? Well, we get the first term will be e to the y minus y. And then we're going to subtract, plug in 0. E to the 0, 1 minus 0. All right, so there's our next integral. Of course, the 0 you can not worry about. The integral of e to the y is e to the y. Integral of minus y minus a half y squared. Integral of minus 1 minus y. And then we'll evaluate 0 to 1. So we plug in 1. That's e to the 1, which is e, minus a half minus 1. Now, are we done? Don't forget, you got to plug in 0. E to the 0 is 1. And now the other terms are 0. So we get e minus a half minus 1 minus another 1. So that leaves us with e. And if you put all these terms together, it's like minus 2.5. Or you can write it as minus 5/2. And that's the answer. So this is a case where changing the order of integration and being careful, it's easy to drop some terms. So patience. It's good to be patient when you're doing these problems. All right, good. Next one, number 4. Find the surface area of the cone z equals the square root of x squared plus y squared above the region R, given by 4 less than or equal to x squared plus y squared less than or equal to 25. Now we could sketch this. That's not so bad to sketch this, because what do you have? You have your space, so here's your x, y, z. We have this cone coming up, and you might say, how do you know it's a cone? Well, my biggest clue that it was a cone was it said it was a cone. Yeah, that's a dead giveaway every time. How about this region? X squared plus y squared between 4 and 25. Well, really that tells us there's 2 circles down here. So you have one circle, the smaller circle, which is radius of 2, all right, and the larger circle, which is radius of 5. All right, so this goes from 2 up to 5. So that's what's happening downstairs. Here's our region downstairs. And yeah, it goes behind. You just can't see it because of the cone. And so what does it look like? So that's our region downstairs. For as far as upstairs, what happens is you can imagine that this comes up to the cone. So we have a lower part, and again this is coming up to the cone, and we have an upper part. Okay? And so what does it look like? Well, if you've ever seen say like a dog after it's had surgery, they put on these little tiny pieces there so that the dog doesn't try to pull out its stitches. Little funnel. That's kind of the shape we have going on. So we're after the surface area of that shape. Okay, good. Whew. Boy, how are we going to find that? And, well, we're going to find it by being patient. We're going to think of this as our function, f of x, y. And for surface area, there's a nice little formula. So surface area, it's the integral over our region R. And as a reminder, R is this part, the downstairs part. The square root of 1 plus f sub x squared plus f sub y squared dA. All right. Now I know what you're thinking. Ooh, this is going to be a polar problem because of, you see the circle downstairs. But hold off. Don't go too far down that road. Let's just be careful and let's see what happens. So, equals integral over our region, square root of 1 plus. Now, if our function, we can write that as x squared plus y squared to the half. That's kind of the more calculus-y way to write it. Write it as something to a power. So, I'm taking the derivative of that, the 1/2 comes down, x squared plus y squared to the minus a half. Derivative of the inside with respect to x is 2x. Then we're going to have that squared plus, similar process, 1/2, x squared plus y squared to the minus a half times the derivative of the inside, which is 2y squared. Okay, good. It's starting to look really bad now. Well, but don't worry. It looks the worst just before it gets totally terrible. Okay, there you go. See? Slightly better, right? We got the 2's to cancel. Progress. Progress. In fact, there's even more progress than that. Because what do we have? Well, what we have is we have the square root of 1 plus. Now here, I can think of this x as being the numerator. That's x squared. And then this, because of the negative exponent, is downstairs. Negative 1/2 times 2 is negative 1. So it's x squared plus y squared. The second term is almost identical, except it's y squared over x squared plus y squared. Now, if you stare at this, but not too long, what do you notice about these two terms? What happens when you add them together? Well, you'll end up with x squared plus y squared over x squared plus y squared, also known as 1. So, we're getting the integral over our region, the square root of 1 plus 1, dA. Now, the square root of 1 plus 1 is also known as the square root of 2. And now you're like, wow, that's amazing. We just have to integrate over our region dA. But wait a second, that's even easier than that. Because, okay, think about it. If we're just integrating over our region dA, what do we actually find? What we find is that this is going to give us the area of our region. Now let's think about what our region is. It's between two circles. So let's think of the outer circle. How much area is in that outer circle, that circle radius 5? Well, pi r squared would say that it's 25 pi. And how much in the inner circle? Radius 2? 4 pi. And so, if we put it together, 25 minus 4 is 21. We still have that square root of 2. And of course, we get a little bit of pi in there. And that's our answer. 21 square root of 2 pi. Oh, what a cool problem. Yeah, it looked like it was going to be terrible, but in fact, because it's a cone, it turns out to be elegant. Beautiful even. Ah, great times. What a wonderful time to be in Calc 3. It's a lovely time. All right, number 5. The Archimedean spiral is given by r equals theta. Let r be the region between the origin and the Archimedean spiral for 0 less than or equal to theta, less than or equal to 2 pi. So here's sort of a quick sketch. So what's happening? So we're going to start here at 0. We go out 0. Now as we start coming out, we get further and further out. So essentially it says the further you spiral, the farther out you go. So this is r equals theta, right? Because the further around we go for theta, the farther out we go. So there's our region, our region capital R. All right, now we're told that our density is thrice the distance to the origin. What does that mean? Well, it means that our density, if I pick any point, oh my gosh, there's a lot of area to shade in here. Okay, it's a big region. All right, so if I pick a little tiny piece, so there's my little tiny piece, and I say, well, how dense is that region? What I would look at is how far away I am. So I could say that my density is equal to 3. That's what the word thrice. Thrice is a very fancy word for saying multiply by 3. Sort of like twice, it says multiply by 2. Distance to the origin. Now, I could write that as the square root of x squared plus y squared, but that would be ridiculous. I wouldn't want to write that as 3 times the square root of x squared plus y squared, because look at our picture. Our picture is given in polar coordinates. We don't want to work in x and y, but more to the point, this has a better expression. It's 3r. Exactly. Something, the kind of problem a pirate would love, because you get to go r. Okay, so how do you find mass? Well, mass, you integrate. It's a 2-dimensional integral, so it's double integral over your region of density dA. So the way we think of it is, if I take a little bit of density, multiply it by a little bit of area, that's the mass of a little piece. And so we say, okay, so here we have the mass of a little piece. And now what's happening is the integral says, let's add all these little things up. So if you add up all the little pieces, then of course, what we'll get is the total mass. All right, good. Life is good. So let's figure this out. Now, we're in polar, so integral, density is 3r, dA, r, dr, d theta. Theta goes 0 to 2 pi, so 0 to 2 pi. R goes from, and you see here, it tells us the origin, which is 0, out to the curve. Well, the curve is r equals theta. All right, cool. So, integrate with respect to r. Well, before you integrate with respect to r, you should, of course, combine those terms. It's really 3r squared. If you integrate with respect to r, what do you get? Well, the integral of 3r squared is r cubed. Evaluate that from r equals 0 to r equals theta. And that's not a bad integral to evaluate. That's 0 to 2 pi theta cubed. Integral of theta cubed is 1/4 theta to the 4th. Evaluated 0 to 2 pi. Plug in 0, you get 0. And I should have said up here, you plug in 0, you get 0. So we're going to get 1/4 times 2 pi to the 4th. If you raise 2 to the 4th power, that's 16, times the 4th is 4, and then of course pi to the 4th, and then we're done. Now you might say, wait, what about units? Well, we can't talk about units because they never gave us units. So it's just 4 pi to the 4th. Units are whatever they turn out to be. All right, that was good. This was kind of fun. You know, if we were still doing quizzes, this is the kind of quiz problem you'd like to get. You know, it's just like boom, 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 comes out, works out in a very nice way. All right, number 6. Find the mass and center of mass of the region R consisting of the triangle with vertices 0, 0, 1, 1, and negative 1, 1 with the density equal y. So let's do a quick sketch of our region here. So we have 0, 0 is there, 1, 1 we'll say is here, and negative 1, 1 is just straight across. So negative 1, 1. And so there's our shape. All right. Now our density is y. What does that mean? Well, that means that at the bottom it's not very dense, but as we start going up, it gets more and more dense. So the higher up you are, the denser it is. Right? I don't know if that's a very convincing picture, but it's supposed to be darker here and lighter there, just to say you're more dense near the top. Now we've got to find a couple of things here. So this problem is going to take us a couple minutes, but that's all right. We've got time. We've got to find the mass, and we've got to find the center of mass. So let's start by talking about the mass. So the mass will be integral over our region R of our density and dA. Now for us, we should think about how we want to integrate. Now, we could slice first up and down. That's perfectly fine in this setting. Or we can slice left and right. Which way do we want to go, and why is it left and right? Okay, so which way do you want to go? Yeah, you're right. We do want to go from left to right. Good, good, good. Why? Well, you might say, it's because our density is y. No, that's a Calc 2 explanation. Let's talk Calc 3 explanation. The reason why it's better to slice from left to right is because as we go from the top to the bottom, we always have a consistent left-hand side and a right-hand side. We never change. If we were going top to bottom, the issue is that we change at 0 what the bottom curve is, which means we'd have to split and do twice as many integrals. Our goal is to do as little work as possible. So that tells us that when we're talking about our dA, our density, by the way, is y. So we're going to slice this way, which means we're going to do dx dy. Now our bounds. Well, we know y goes from the smallest value of y is at the very bottom here, which is 0. The largest value is at that top. So we go from y equals 0 to y equals 1. What about the left and the right? Well, on the left hand, this line is the line y equals minus x, which we could also write as x equals minus y. On the right, 0, 0 to 1, 1, that's the line y equals x, which also, true fact, it's x equals y. Now these are x bounds because it's dx associated with that layer. So we're going to go minus y to positive y. All right, so we're getting close. So let's see what we get. Okay, so 0 to 1, integrate that with respect to x. We're going to get x times y, evaluated from negative y to positive y. Now, if you plug in positive y, you'll get y squared. Subtract minus y squared, which really says that this is integral 0 to 1 of 2y squared. Okay, I should really have said x equals there. It's useful to write those in, just so you remember what's being evaluated. All right, so that gets us 2/3 y cubed. Evaluate that from 0 to 1. And therefore, 2/3, again, that's our mass. And that's part of our answer. Okay, so now we're ready to go into phase 2. What's phase 2 of the problem? The center. Now, center of mass, there's really 2 parts. One part is easy. X bar is 0. Why? Symmetry. What do we mean? Well, if you come to our picture and you look at our picture, you see that there's this nice line of symmetry here. So, in particular, it's symmetrical in the following sense. If you were to pick this up, turn it over, and put it back down, it'd be the exact same shape, but not just the exact same shape, it would also be the exact right density. In other words, you wouldn't have been able to tell. That's what I mean by symmetry. It means if you do some operation, it's like, did you do anything? And if the answer is no, it's the same as before, then, aha, you're good to go. All right, cool. So that makes it halfway done, right? But what about the y bar? Well, there's no symmetry. Other than the one we've already talked about. So it means we have to do work. But that's okay. That's fine. What we really need to do is that y bar, it's that moment with respect to the x-axis divided by our mass. So we got to find that particular moment. So it's something divided by 2/3. Okay. And, all right. Hopefully that's enough for us to figure out what that ends up being. We just need to figure out what goes there. So that moment with respect to the x-axis, so the way we do moments is, it's a very similar process. You have a density, but you also have a location. And location is relative to the axis you're talking about. So for us, we're going to have the same bounds. It's the same region. The only thing that really changes is you add an extra piece. Now for us, what's our extra piece? Our density is y. What's our location? So in other words, we're thinking of, here's a little tiny piece. What's our location down to the x-axis? So the answer is y. Aha! Y. This question really gets after the y. So we're going to integrate y squared and dx dy. Now this will feel very similar to what we just did. And the reason it's going to do that is because it's very similar to what we just did. And so that's a good reason. Xy squared, evaluate x equals minus y, x equals y. So you're going to get y cubed minus a minus y cubed. So that's the integral 0 to 1 of 2y cubed. And if you integrate that, that'll be 2/4, also known as a half, y to the 4th. Evaluate that from 0 to 1, which is a half. Now, this is not the center of mass. That's the moment. So we have to take that moment, which is a half, divided by 2/3. Well, that's really the same as 1/2 times 3/2, which means that we get 3/4. Now, that would say x bar equals 0, y bar equals 3/4. So our center should be 0, 3/4. You should always pause for a second and ask the question, is that reasonable? Is it? Well, if you think about the picture, it says we want it to be 3/4 the way up. So maybe roughly right there. Now, first off, it's good it's between 0 and 1. If it had been like 2, trouble. Negative, really bad trouble. But also we see, look, it's biased towards the top. And why should we expect that? Well, first off, it's a little bit more region up at the top. But the other thing is it's also heavier at the top because it's denser. So yeah, it is fairly reasonable that there should be a definite bias towards the top. which is good because not only is it reasonable, that is the right answer. So that's good. You know, you always like it when you get the right answer. It's much better than when you get the wrong answer. All right. Number 7. Find IZ for the region between the origin and the Archimedean spiral r equals theta. But now theta goes from 0 to pi, and the constant density of delta density is 1. So boy, they really like the Archimedean spiral here. Now we only have to have the bottom half. So here's our r equals theta, and so that's our region. So all right, so what is the IZ? Well, you might think when you look at this picture, that's weird. There is no z. This is like a two-dimensional picture. Normally we would think of this as our xy. So what does the IZ stand for? Well, so this is the I, that stands for inertia. The subscript here says relative to what? So that's when we have a subscript, we're saying relative to. Now, how does z fit into this picture? And the answer is z is right there. So it's just a fancy way of saying really with relative to the origin. It's like you imagine that you came here and you stuck the z-axis sticking right out of that paper. Okay, so how do you find inertia? Well, good news, there's a formula for that. Actually, for almost everything we're going to do, there's a formula for it. So we're going to integrate. It's a two-dimensional region, so it's a double integral over our region. We're going to have our density, and then the dA. This is the mass. Then there's one other piece, and that is location squared. So inertia is sometimes called the second moment. The second refers to this exponent. Okay, so, all right, good. So, our region, well, we're going polar again. No surprise, given our region is described in terms of polar. Density is 1. Now, location says, you think of taking a little tiny piece and say, how far is it from the origin? Well, it's r squared, because the distance is r, so r squared. dA is r dr d theta. Theta goes 0 to pi. R goes from 0 to theta, because we're going out to r equals theta. Well, all right, so that's really integrating r cubed. So this is 0 to pi, integral of r cubed dr, 1/4 r to the 4th. Evaluate that from r equals 0 to r equals theta. That is 0 to pi of 1/4. Whoops, I forgot my d theta there. Ha 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 ha. Well, that's why you always check. Notation is really important, especially once you hit Calc 3. And I know at Calc 1 it feels like, nah, notation, schmotation. But in Calc 3 it's like, yeah, respect the notation. Okay, integral of theta to the 4th. Well, we're going to end up with theta to the 5th and divide by 5 in front. Evaluate from 0 to pi. Of course, the 4th times the 5th is 1/20, and pi to the 5th is pi to the 5th, and if you plug in 0, you get 0, and there's our answer. By the way, this actually came from an old final exam, and on the old final, we even said, oh, hint, this is how you compute the inertia. I gotta say, the students really like that problem on the final. It's kind of surprising, and yeah, you know, occasionally we make a mistake and get a problem that students enjoy, but you know, we're trying, we're only human, we do our best, and then, well, that's all you can do, right? Okay, good. Well, we're getting pretty close here. We're doing great. Let's do number 8. Let R be the set of points where x goes from 1 to 2 and y goes from 0 to 1, and our density is x. So actually that's that's a little tiny square. It's kind of been shifted over though. So let's see, 1 to 2 and 0 to 1. So here's our region. So here's our region R, and our density is x. Well, what does that mean? Well, that means that the further out you go in the x direction, the more dense it is. So over here, not very dense, but on that right-hand side, very, very extremely dense. Right? Okay, so we're more dense to the right. Good, good. Find the inertia. Okay, that's not so bad. When we rotate around the line, x equals y. What? Wait, what? Now we've talked about inertia. That's weird. Because the reason I say is it's not inertia with respect to the x-axis, and it's not inertia with respect to the y-axis. It's inertia with respect to this line here. This is the line y equals x. Well, let's just start with our basics and we'll follow our nose and see how far we can get before we get stuck. So, according to our formula, our inertia, and we'll put down y equals x, I don't know. We need to say with respect to what, right? Okay, so that's the integral over our region, our density. Then we have our location. By the way, sometimes I write location, sometimes I write distance. It's really the same thing. It's just a matter of, when I say location, it really says it's okay to be negative. Oftentimes when we write distance, we really mean positive distance. But all right, dA. Okay, so let's just sort of fill in the blanks. Now, this is going to be, it's such a nice square region. It's going to be Cartesian. Cartesian is made for things that are rectangles. Okay, so integral. We'll figure out the bounds in a second. The density is not bad because it's given to us. It's x. We've got to think about this part, the location. So somehow it's like, here's my little tiny piece. So I need to figure out how far is it from this little tiny piece out to this line, y equals x, or x equals y. Well, it would be nice to know the distance between some arbitrary point, I don't know, we could call it A, B, and the line. Is there any way we could figure that out? Well, oh, wait a second, hold on, there was the distance between A and B. Oh my gosh, it's exactly what we need. It's like they wanted us to know stuff, but we had to understand how we were going to use it. See, that's this piece of information, that location. It's the distance. So it says, okay, if I want to know the distance from this little piece to that line, I take the difference in the coordinates, right, A, B, difference in the coordinates, and I divide it by root 2. Now that says, okay, so I'm going to take absolute value of x minus y over root 2. Now that's, if I were thinking of this as a particular point x comma y, that's this part right here. How far is it? That's the distance, or if you like, that's the location, squared. Good. Now, let's go ahead and get the bounds in there. Do you want to do dx dy or dy dx? Dealer's choice. Which one? I don't know. I don't think there's any big preference one way or the other. So, okay, we'll do dx dy. So where does y go from? Well, yes. You know what? Staring at this, I've changed my mind. Now, you're probably thinking, really? That doesn't shock me at all, Steve. But let's think about it. So there's something I said a while back, and I'm going to say it again today. And you probably know where I'm going with this, but remember, there's a nice rule to always keep in mind, which is 0 is a friend. So whenever we can get 0 involved in a problem, we should. And moreover, the sooner you can get 0 involved, the better. Now look at your bounds. You got a 0 there. So what would be ideal is if we could get that 0 in as soon as possible, which means we want the inner layer to be with the y, so that we could get the 0 in sooner. The outer layer will be an x, 1 to 2. Okay, so we're still going to be a while before we can integrate. The nice thing is if you square the square root of 2, that's going to be a half. And that's a constant. I can pull it out all the way in front. So a half, integral 1 to 2, integral 0 to 1. Now, x minus y quantity squared. Let's do a little bit of computation here to the side. So x minus y squared, that's x squared, minus 2xy plus y squared. Excuse me. So that's the part that says, because we pulled out that square root of 2 squared, that's the half. So you get the x squared minus 2xy plus y squared. Notice the absolute value you don't care, because you're squaring. So the absolute value doesn't mean anything. Now multiply it by x, and we end up with x cubed minus 2x squared y plus xy squared. dy dx. And now we're ready to begin. So, we have a half, integral 1 to 2. Integrate this with respect to y. Integral of x cubed with respect to y is x cubed y, because x cubed is acting like our constant. Minus 2x squared y, well, minus 2x squared is a constant. Integral of y would be y squared over 2. So we can actually cancel off the 2, so it's x squared y squared. And the last one we get plus x y cubed, then we divide by 3, so that's 1/3. And we're going to evaluate that from y equals 0 to y equals 1 dx. So plug in 0. The nice thing is you get 0, 0, 0. So we need to only plug in 1. So that's a half integral 1 to 2 of x cubed minus x squared plus 1/3 x dx. Making progress. Okay, so 1/2 integral of x cubed, 1/4 x to the 4th. Integral of x squared, 1/3 x cubed. Integral of 1/3 x, well, 1/3, then there'll be another half, so 1/6 x squared. Evaluate from 1 to 2. So we end up with a half times, okay, this is going to take a while for us to work through. So 1/4 times 2 to the 4th, and we'll write that as, say, 16/4. 1/3 times 2 cubed, so minus 8/3. 1/6 times 2 squared plus 4/6. Subtract. We'll get 1/4. Subtract 1/3 plus 1/6. All right. Now, common denominator. What's something that divides into 4 and 3 and 6? Well, 12 does that. Okay, so we have a half. And then we're going to have everything in terms of twelfths. So we'll start here. 16/4. Going to multiply top and bottom by 3, so that becomes 48/12. 8/3 multiply top and bottom by 4, so minus 32. 4/6 multiply top and bottom by 2, so plus 8. Now here's where you got to be careful. This is why parentheses are your friends, because that minus goes all the way through. So don't forget about that minus. So the 1/4 becomes 3/12, but it's going to be subtracted. The minus 1/3, minus minus makes it a plus. That'll be 4/12. Then minus 1/6 becomes minus 2/12. Okay, so let's be careful. 48 subtract 32, 16. Plus 8, 24. Subtract 3, 21. Plus 4, 25. Subtract 2, 23. So upstairs we have 23. Downstairs, 2 times 12 makes 24. And that's the answer. 23 24s. Just like what you expected. No. Now that one, you got to work on this one. You got to be really patient with this one. Lots of chances to make mistakes towards the end. And of course, you also got to know how to start it. So yeah, this one's a double whammy. It's not so easy to start, and it's a little bit, you got to be careful at the end. But of course, once you get there, it's kind of satisfying. Like, hey, we got it. And this shows you, you know what? You can do more interesting things. You don't always have to be constrained by, oh, I've always got to be around the x-axis. Oh, I always got to be around the y-axis. It's any line. An axis is just a line which happens to have an easy description. But we shouldn't let that stop us from thinking about doing other things. All right. Number 9. So, consider the planar region where x is less than or equal to 1, y is less than or equal to 1, and x plus y is greater than or equal to 1. Let's see if we can figure out what that looks like. So, we draw some axes here. So we say, okay, here's 1. And so here's the line x equals 1. Whoops, where do we want to be? Well, we want to be less than or equal to it. So we're on that side of the line. Here's 1 here. This is the line y equals 1. And we want to be less than or equal to it. So we want to be below. So we want to be both to the left and below. And we have this line x plus y greater than or equal to 1. Now, what is x plus y equals 1? Well, it's going to cross here on the y-axis at 1, and it's going to cross on the x-axis at 1. And it turns out it's a line. So it's this line here. Whoop, pretend that's a line. So this is the line x plus y equals 1. Now, which side are we on? Well, because we want to be greater than or equal to 1, if you're not sure, here's the thing. Just pick a point. 0, 0. Is 0 plus 0 greater than or equal to 1? No. So it means we're definitely not including that point. So this side is the wrong side. So we don't want to be here. We want to be there. Okay, so let's recap. To the left, below, and above Mr. Slanty. So what's our region? It's this triangle here. Of course, we should have suspected it was this triangle because once you draw it, it's the only part that's actually a bounded piece. And I think we want to avoid unbounded things for the time being. Not that we can't do it, it's just probably better to avoid it for the time being. So, what's our question? Find the value alpha so that if our density is x plus alpha, then the inertia with respect to y is 1/3. All right, so that's saying that our inertia with respect to the y-axis. So somehow the inertia is something to do with spinning. So if we were to somehow spin this around y, we get this inertia coming in. So where do we start? Well, we know that 1/3 equals our inertia. Well, integral over, so this is the integral of our region. And again, we have our pieces. We have our density, and we have our location, which again, location is just a fancy way of saying distance, dA. So the mass square of distance. All right, so integral, our density is x plus alpha. Our location, well, if I'm at a little piece here, how far is it to the y-axis? Well, it's x. So our location is x, so x squared. So that's what we have to integrate. All right, so now the question, what's the order of integration? I don't think there's really any clear answer, but since everything is here is x, let's do it dy dx. And the reason why I say there's no clear answer is there's kind of symmetry here, and so whether you go y first or x first, it's more or less the bounds are going to look almost identical. But if we integrate with respect to y first, at least that's a really easy integral. So let's talk about bounds really quick. Where does x go from? In other words, what's the smallest value of x? What's the largest value of x? The smallest value is 0, and the largest value is 1. Now, suppose I've picked my x, so here's my x. Now, where does y go between? Well, I'm going to go from this line up to y equals 1. What's this line? Well, solve it for y, it's 1 minus x. Okay, so what do we have? Well, let's do one more thing. 0 to 1, 1 minus x to 1, multiply that through. That's x cubed plus alpha x squared and dy dx. So, this will be 0 to 1. The x cubed plus alpha x squared is a constant. There's no y involved. So y, evaluate that from 1 minus x. This is y equals, there we go, up to y equals 1. There we go. Okay. Good. Now, at first this looks terrible, but wait a second before you get too nervous. So you get x cubed plus alpha x squared. Now, let's evaluate this part. Y equals 1, subtract 1 minus x. Now what do you see happening here? 1 subtract 1 minus x, also known as x. So if you multiply that through, that becomes 0 to 1, x to the 4th plus alpha x cubed dx. Well, now we integrate. 1/5 x to the 5th plus alpha over 4 x to the 4th, and you evaluate that from 0 to 1. The nice thing is when you plug in 0, you get 0. What happens when you plug in 1? You're going to get 1/5 plus alpha over 4. And remember, if you follow this back all the way, that equals 1/3. So, we're almost there. Alpha over 4 would be 1/3 minus 1/5. Common denominator would be 15. So that's 5/15 minus 3/15, also known as 2/15. And, oh, we're almost out of space. Okay. And so we can finally finish off, multiply both sides by 4. So alpha should be 8/15. And there you go. By the way, this little part here, it's one of the nice things. It's oftentimes we have a tendency to like, oh, let's expand out as soon as possible. Sometimes if you're patient, you say, well, let me not expand everything right away. Let me do a little bit more closely, a nicer examination. Oftentimes you'll see that things are a little bit better than you thought they might be. And of course we like it. We like it when a plan comes together. Okay, so that's number 9. Which brings us to our last problem. Well, don't worry, there's going to be more. It's just our last problem for today. There will be always more problems. Okay, so let E be the solid lying below the plane z equals y over 2. So in case you're wondering where that is in this picture, because this is actually the picture here. So, and it says to the right, but that's because that's a typo. It really should be see the picture to the below. But okay. So this is z equals y over 2. All right. And the vertices are at 0, 0, 0. That's this one way back here. At 3, 0, 0. So that's at x equals 3. And then y and z are both 0, and then 0, 4, 0 is over here. So there's our picture. It's a nice tetrahedral shape. And now what do we have? Well, the density is given by x. So that says over here on this end, it's like super sparse. It's like that amazingly sparse gel they used to catch fragments of meteors. Over here, it's very dense, very heavy. And so that as you go from left to right, it's a lot more dense over there than it is there. Now, okay, so we know our density. Find the mass. So this is a mass problem. All right, well, we kind of know where we're going. So where are we going? Well, if we're after mass, it's the integral over our shape, and in this case our shape is called E, of our density dV. So our density, well, that's x. What's dV? Well, because we have no other, suggestion, our default order for dV, if we don't have any other reason to pick an order, then the order we should go in is dz, dy, dx. Now, it's not because dz, dy, dx is somehow more sacred, it's more what we're used to. We've sort of been building up. Okay, we're used to thinking y is a function of x. We're used to thinking of z as a function of x and y. And that's what this order is built for. All right, so we've got to take some time, and I think most of this problem is really about setting up the bounds. So we're going to do an integral, x, dz, dy, dx. So since my last layer is z, I'm going to start by looking down the z-axis. And when I look down the z-axis, what I'll see is just something in the xy plane. And well, it's not so hard to figure out what I see. I hit here at x equals 3, I hit here at y equals 4, and I get a triangle. So that's my picture here in the xy plane. So let's talk about our bounds. Maybe let's talk about where we go for x. X goes from 0 to 3, because I can see lowest value for x, highest value for x. How about y? Well, so if I pick a value for y, if I pick a value for x and let y move up and down, well, I'm going to move between this line, which is the line y equals 0, up to that line, that slanty line. Well, what is that? Well, this is, well, we know the y-intercept is 4, and then we go down 4 over 3. So down 4 over 3 minus 4/3 x. So that's our 4 minus 4/3 x. Now, how about where does z go from? So go over to the three-dimensional picture. If we're looking about z, that means we want to go up and down, parallel to the z-axis, up and down. So going up and down, well, we're going to start, and then we're going to go up. So, right, we're going to go in between. So our bottom part is the xy plane, known as z equals 0, and our top part is z equals y over 2. It's that slanted plane we began with. So y over 2. Now we're ready to integrate. We've done our setup. So, I wonder what this will turn out to be. 0 to 3, 0 to 4 minus 4/3 x. Ugh, I'm thinking this is going to be a terrible answer. Well, we'll keep going. So the integral of x with respect to z is x times z, going from z equals 0 to z equals y over 2, and dy dx. Well, the nice thing is pretty easy because you plug in 0, you get 0. You plug in y over 2. So we go 0 to 3, 0 to 4 minus 4/3 x, xy over 2, dy dx. Well, okay. The next layer is still not too bad, right? Because what is that going to be? Well, integral 0 to 3. If we integrate this with respect to y, there is a y there. So we're going to end up with xy squared over 4, because y squared divided by 2, there's already a 2. And we're going to evaluate that from y equals 0 up to y equals 4 minus 4/3 x. Okay, so what is that? Well, that's integral 0 to 3 of x over 4. And then we have y squared, which is 4 minus 4/3 x squared. Then we're going to subtract. Oh, good news, we're subtracting 0. Oh, for a second there I thought we'd have to do something crazy. Well, we still have to do something. Okay, let's square it. Let's see where we get. Okay, 0 to 3. So we have x over 4. So let's be careful, work our way through it. 4 squared, and 16 years ago. Oh, wait, no, that's something else. That's 16. 4 squared, okay, then minus, that's my a squared, minus 2ab. So minus 4 times 4/3 x times 2 will give us 32/3 x. Then plus, we've got to square that term, 16 over 9 x squared. All right, so multiply the x over 4 through. X over 4 times 16 will give us 4x, and that's not so bad. X over 4 times 32/3, well, that'll be minus 8/3 x squared. 16 over 9 times x over 4, well, that'll give us a 4 over 9 x squared. Okay, all right. Maybe we can figure this out. Maybe it's not so bad. Okay, piece by piece, integral of 4x, right, 2x squared. Integral of 8/3 x squared, well, it's going to be x cubed. Divided by 3 makes it 8/9. Whoops, why did I put x squared there? No, see, that's x times x squared. That was really an x cubed, you just couldn't see it. Okay, integral of 4/9 x cubed, well, it'll be x to the 4th, but we're going to divide by 4. We already have a 4 there, so 1/9 x to the 4th. And evaluate 0 to 4. All right, we're almost there. Now, what? 0 to 3. Oh my gosh, I had too much 4s on my mind. 0 to 3. Well, all right, I might be able to squeeze it in right in the very bottom here. Equals, okay, plug in 3. 2 times 3 squared. It's 2 times 9, which is 18. 3 cubed is 27. Divide by 9 is going to be 3 times minus 8 is minus 24. Then 3 to the 4th is 81. Divided by 9 is 9, so plus 9. 18 plus 9 is 27. Subtract 24 leaves us with an unusually nice answer, 3. Wow, that was actually even better than we could have hoped for when we started. Well, don't give up. Don't give up. Even if things look bad, it could get better. It oftentimes does get better. So that's what we hope for all of you. We hope you're doing well, and we hope for all of you that things get better. So take care, my dear friends, and we'll see you in the near future. All right, bye.